Hey there, this is going to be some information for you about Lesson 5.5 in your Pearson Algebra 2. True or false? 1 and -1 are roots of the equation x squared equals 1. Well, one thing you can do is you can test to see if they both make true statements. Is 1 squared equal to 1? Yes. How about -1 squared? Yes. True. The equation x squared minus 4x plus 4 equals 0 has roots 4 and -4. True or false? Well, something different you could try here would be to factor it. I need factors of +4 that add up to -4. Well, strangely enough, I get the same factor twice. So when I go to use the zero product property, I will only get one solution, x equals 2. So therefore, these two numbers are not roots. So we have a giant theorem that says the highest power of our polynomial, the degree of our polynomial, tells us how many roots we have. So in this case, it would be 5, and here it would be 1. What are the possible rational roots of this polynomial? So we have a theorem that says that we take factors of the constant. Okay, so we call that P. We're going to identify P and Q. Sorry. The constant P is 8, and the leading coefficient Q is 15. Okay, so don't be thrown off by P and Q. Those are just, I don't know, that's just part of the theorem. So the theorem says we need the P's over the Q's. So factors of 8 would be plus and minus 1, plus and minus 2, plus and minus 4, and plus and minus 8. Factors of the leading coefficient, 15, would be plus and minus 1, 3, 5, and 15. Okay, so what I like to do is make a list. So all of these terms divided by 1 would be themselves. What about all of these terms divided by 3? Well, I would pick up 1/3. Ooh, lots of choices. 2/3, 4/3, and 8/3. What about each one of these divided by 5? Oh, a whole bunch more. 1/5, 2/5, red fish, blue fish, 4/5, 8/5. And lastly, all of these terms divided by 15. Good grief. 1/15, 2/15, 4/15, and 8/15. Okay, so this is a big list, and what this means is if this graph crosses the x-axis, let's say it looks crazy like this. If this graph crosses at any places that are rational numbers, it must be a number on this list. Now, this is a pretty big list. Okay, the graph could cross at completely irrational numbers. It could cross over here at the square root of 17. Who knows? It could cross here at pi. Not sure. But if it crosses at anywhere rational, it must be a number on this list. So I could even say to you, is 2/5 a possibility for where this graph might cross or where this would have a solution? Yes. It's on my list. What about 5/4? No. The graph cannot cross at 5/4. I think that says -1/5. Yep, that's on my list. And what about 2/3? Yes. That's a strange theorem. Okay, what are the rational roots of this? Well, I'm not sure, but let's go through our P's and Q's. So Q is 2, P is -6. So factors of 2, plus and minus 1, plus and minus 2. Factors of 6, plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. Now I usually do this sort of in the opposite order. So I do P over Q. So 1, 2, 3, and 6 divided by 1 are all themselves. And then each one of those divided by 2, I would get 1/2. 2/2 is 1, so I already have that listed. 3/2 is a new one. And 6/2 is 3, which I already have listed. Okay, so definitely the graph cannot cross at 0. -1, yes it could. 1/3, I don't think so. And 1/2, yes it could. All right, that's a big bunch of theorems. I'm going to take you on to part 2 soon.